Hello. From this video onwards, we will try to explore how neural network learns. So basically, we'll be talking about two very famous algorithm called the gradient descent algorithm and the backpropagation algorithm to discuss different stuff about how neural network learns and those stuff. So we will try to deep dive into those concepts. Maybe we will try to understand the mathematics behind this one as well. So I'll try to make it as simple as possible. Now we'll take an approach something like this one. We will take a very simple example, and using that example we will try to understand all of these concepts. Now this video will be part of this deep learning ML3 playlist. So if you are following this particular playlist, these videos like the introduction of the deep learning and the intuition behind the neural network will work as a basis of this particular video. Also, we already discussed like different kinds of tensors and their operations, right? So this will also form a good basis for this particular video and next few videos. Okay, now we will first start with a problem statement. So we will take the very simplistic problem of deep learning called the handwritten digit recognition problem. So the problem is something like this one. So we will have some handwritten digits. So the job of the neural network will be properly classify these digits corresponding to their digital versions. Like if it is a 0, so it should classify this one as a 0, it should classify this one as a 7, something like this one, to their proper classes. So this problem sometimes called the hello world problem of deep learning, because it is not so simple and it is not so complex as well to implement. So at least we can implement this one with a single hidden layer feed forward neural network, properly connected neural network. Okay, so now we will see those designs as well in future slides. And what we'll be doing is basically we will try to create a simple neural network classifier which will basically classify these handwritten digits into their corresponding classes. Classes means their corresponding digits here, right? Now this is a classifier because this is in machine learning, this is a classification problem, right? Now in neural network it is possible to have regression problem as well. We will see in the future videos, but this particular handwritten digits recognition problem is a classification problem, so that's why we'll be building a neural network classifier over here. Now before we jump into the neural network architecture we'll be using, let's try to analyze how we humans are process this kind of information. Because if you see a kid who is basically, let's say if a 4 years old kid can recognize these handwritten digits with 100% efficiency almost, right? So how it process the information. So if I just try to analyze this one, so from our eyes this information goes through this thalamus and then goes to the rear part of our brain where we have our visual cortex area, right? The visual area, which is actually responsible for all the visualizations or basically all the visual stuff our brain do. So if we just try to take a closer look at this particular area I'm talking about, so you will find this kind of structure. So you will see like this particular area is consist of different sub areas like v1, v2, v3, v7, something like this one. So now I am not medical science expert or a brain expert. What I am trying to analyze over here is this architecture, this particular architecture, whatever we have, whatever we will try to understand from this particular two images. Although our brain structure or architecture is way complex than this one, but whatever we will try to understand from this slide, we will try to implement the similar stuff in our neural network. Okay, so if you see this areas over here, right, this areas in this visual cortex area, so it's subdivided into a lot of smaller areas like v1, v2, v3, this one. So each and every area actually process different kinds of information like the motion or the relay signals or like color and forms, this kind of stuff, and they pass signals from one area to another area, the next area over there. Kind of, if you are following the neural network videos I created, we talked about the hidden layers, right? So maybe we can draw an analogy on these areas to our hidden layers over there, right? So maybe when in the next couple of slides we'll talk about the probable architecture we can thought of for this particular digit recognition problem. Maybe we will see an similarity between the structure we have in our brain and what kind of structure we thought about the neural networks as well. But neural networks are way simple compared to how our brain process informations, because this is nothing but a supercomputer we have in our brain. So let's move on. Let's talk about the initial design we can think of this particular problem. So if you remember the video, I talked about the neural network intuition and the neural network design, initial intuition about the neural network. We talked about this kind of diagram over there. Probably I'll give the video link somewhere over here so that you can go through it again. So this is a very simple feed forward network architecture where we have some kind of input layer, right? So if we talk about the handwritten digit recognition problem, so what will be our input? Our input will be images, right? Handwritten digit images there, right? We will see from where to get those images and how to process those images. In very simple term, it will be images. Now what will be this x1, x2, x3 values? So these are all the input values for each and every neuron over there, right? So we can think of these values as each and every pixel value of the pixels of that images, correct? So if the images has 100 pixels, we can have 100 neurons as our input layer, and we can pass those pixel values over there. Okay, we'll talk more about this one, and we can assign some weights. As you remember, like in neural network, it's nothing but weights and biases. Even in that particular video, I talked about the concept of bias as well, right? Which works as a threshold of whether this particular neuron will fire or not, right? So what we generally do, we basically take a dot product of this input values and their corresponding weights. We add it to the bias and we pass it to this neurons over there, something like this kind of structure over there, right? So we'll always try to remember this structure over here. So we will basically take the dot product of these two guys, add a bias, take the sum basically, because bias plus dot product of these two guys, then we pass it to a function. It could be a sigmoid function or any other kind of function. We talked briefly about sigmoid neurons as well, right, before, and then we will get an output from that particular neuron. So this is a structure of a single sigmoid neuron, right? So this and this portion of our network is, I just given some kind of layers just to show it as a hidden layer, and each and every layer may do different kinds of work over here, right? So, and each and every layer will have this kind of structure, right? So all layer will have the neurons. So I have not drawn this one just to make it simple, and then we'll have our output layer as well, which will basically generate the output. Now when we'll talk about this handwritten digit recognition problem, and when we will try to train our neural network with this images over there, so what will be our goal? Our goal will be this output should recognize what kind of digits I am giving as an input over here, digit image I am giving as an input over here, right? So for that, to train the neural network, if you see for a particular image, these values will be always fixed, right? So what is basically governing the output is the weights and biases. So if we maintain, or if we can determine the proper weights and biases of this particular neural network, which will properly identify this input image in our output, so then we are done, right? So to achieve that, how we can do it? We need to basically loop through multiple iterations, right? And to determine how close we are to the actual output. So that's why measuring the loss. So basically here, whatever output we are generating, we are trying to determine how close we are, correct? So then that's the loss measurement we are, and our aim is to minimize that particular loss, correct? So that we can optimize our neural network over here. This step is actually called the loss optimization. So based on these things, what we do is we basically calculate the newer weights and biases, and then again go through this one, and again generate the output. So if our output is getting closer and closer to this actual input, okay, so that's the scenario you want to achieve over there. And this thing we need to achieve not only for the single image, we need to achieve for all the images we'll be using for our testing, correct? So this portion, like the way it process this input signal to generate the output signal, called the forward pass. And this portion over here where it basically determines the loss and try to optimize the loss is called the gradient descent. This is how the neural network learn. And to calculate the gradient, there is another algorithm called back propagation. Maybe we'll try to go through that one as well. So these two algorithms are getting involved. So by using these two algorithms, we basically generate the new weight, which is again then feed forwarded to this one, and then it goes on, okay, until we basically get closer to this. Our loss is, we cannot minimize the loss further, that stage, okay. So this architecture we will try to follow over here. Now let's try to think in terms of the digit classification problem, right? So handwritten digit classification problem. So what will be our input layer? So we already had brief idea about this one. So our input layer, we will be passing a kind of image. Now the database, the data we'll be using is called the MNIST data. In that particular data set, so the images are all 28 by 28 pixel size. So that means, and these images are actually grayscale images, okay. So let's see what grayscale images looks like. So if we go to Wikipedia, so grayscale images are something like a black and white images. Now main fundamental stuff about this one is their pixels. If you see, the pixel is a single sample representing only the amount of light that is carries. That means the intensity information. So if we go back to our slide, so for this one, let's say for this particular pixel, so it is a white, right? So the grayscale value will be 0. That means white is pure. That means the grayscale value will be 0. And the pure black, this particular pixel value will be 1. So in between, whatever color intensity it will find, it will assign the values correspondingly. So it will be always between 0 and 1. 0 will be pure white portion and 1 will be pure black portion over here. Now as this particular images will be 28 by 28 pixel, so what will be the number of neurons in our input layer? So it will be 28 into 28, that means 784 neuron we need to represent the input layer over there, okay. Now we will talk about how to represent this one mathematically as well, but at least fundamental wise, this is how it will be looking like. Now let's talk about the hidden layer. So in our input layer, we already have 784 neurons. Now hidden layer is something where you can do experiment. So we'll start with 15 neurons there, and based on our experiment, we'll try to increase or decrease it over there, okay. Now this is how it will be looking like. So from each and every input layer, the data, the output, so here we are passing the weights and the input images pixel values, and that the output will be passing to all the hidden layer neurons over there. That is how a well-connected neural network works, right? So similarly, from the other neurons also in the input layer, the output will be passing to all the hidden layer neurons over there. Okay, I think I forgot to draw from here to here and here to here. I think you get the idea over there, right? So hidden layers will be getting this kind of information. So for our case, we are having 15 neurons over there. We will go with this one and then try to experiment with this one. And then what will be our output layer? So this will be interesting. Now for this handwritten digit recognition problem, we can think of output layer is something like this one. So if you see, I have taken 10 neurons over here, right? So 1 2 3 4 5 6 and then 4 10 here. So now we can think of couple of way of representing this one. So this is one way, and we will go with this way as well. Maybe in latter part, once we understand all this mathematical details behind this one and created a neural network, maybe probably using Google TensorFlow, we'll come back to this problem again and try to implement the second solution here. Okay, so if you see, like, we can think of two ways. The first way will be, so as we have 10 neurons over here, so whenever, let's say, first neuron is firing, let's say if we have 10 bulbs over here, if the first bulb is only on, rest of the bulbs are off, we will think of it as a 0. That means whatever image we have provided over here, the image is a image of 0 over here. Similarly, if this particular neuron is getting fired and the rest of the neurons are not firing, that means their values will be 0, the output values will be 0, and only this one is 1, we can think of the image we have provided is 1. Similarly for 2 as well, other stuff, then 8 9 as well, correct? So this is our output layer. Now instead of 10 neurons, we can think of 4 neurons as well, if we represent this one as a binary digit. Okay, 2 to the power 4, that means at least we have the space for classifying the 10 digits over there, right? And we'll be needing in that case 4 neurons over here in the output layer. We cannot take 3 neurons because 2 to the power 3 is 8, so we can classify maximum till 8, but we need 9 as well over there. That's why 2 to the power 4. Now how we will be classifying it? So if, let's say, if it is 2, that means 0 0 1 0, that means there will be the first 2 neurons will be value of 0, and the third will be 1, and the fourth one will be 0 over there. Similar kind of output for the others as well. Okay, so that could be another design as well, but we will go ahead with this one, and then probably in latter part we will work with the second design as well. So this is my output layer, and where we have our 10 neurons, correct? Now let's talk about where to find the data. So as I said, we will be basically working with the MNIST dataset. So if we see the Wikipedia, so it's a very huge collection of handwritten digit images, specifically from the US Census Bureau employees and high school students. These two kind of age group, they have taken the handwritten digits from them and created this particular data set. So it has almost 60,000 training images and 10,000 testing images. So what we'll be doing is we will be training our neural network with this 60,000 images and then try to test it with this 10,000 images. Maybe if we are achieving higher accuracy, maybe we will try to test it with our own handwritten digits and see how it goes. And if you see, each and every image is a 28 by 28 pixel grayscale images. Okay, so that's why we have taken that example over there. Now if we just go deeper and try to think mathematically now how our neural network will be learning, so we are basically going inside now to formalize the gradient descent and other algorithms. So we need to understand a couple of concepts, but before that, let's try to take some kind of notation so that we will not get confused ourselves. So whatever image data we will be passing as an input to the neural network, we'll consider it as a X. And whatever output it will generate. Now there could be two things over here when we talk about outputs. One is because we are talking about the supervised way of doing the deep learning or machine learning over here, right? So that means those images are labeled. So whatever images from the MNIST we will be downloading it or will be working with. So let's say if it is having an image of 9, so that there will be a label called 9 against that image, so that while training it we can use that to optimize our neural network, our cost function over there. Okay, so let's say that actual output is yx over here. Okay, so when you talk about input neuron or input this one over here, as I said before, the number of neurons we need is 784 neurons over here in our input layer, correct? Now if we just want to translate this information mathematically, so our x will be a 784 dimensional vector over here. We already understood what vector is. Maybe I will provide that video link over here. So that's my 784 dimensional vector. So it will be very hard to visualize that one. At least if it is 3-dimensional we can at least visualize, but 784 maybe we will not be able to visualize it. But in next video we'll try to get an intuition about this one. Okay, now what will be the mathematical representation of our actual output or yx? So it's nothing but a 10-dimensional vector over here, correct? Because we have 10 neurons over here. So let's say we have provided an image of 9, so this is actual output will be 9 as well, right? So in that case what will be the value of yx? So all will be 0 except the last neuron which will be getting fired. And I have given a transpose over here because if you remember from my vector and matrices video, when you talk about vector, we will always, and that too mathematically, we will always consider it as a column vector. Okay, so that's why as I have written it as a row vector, so I have taken it as a transpose so that it will make it as a column vector. So nothing fancy over here. Okay, now let's go further. So now let's talk about how the neural network will be learning. So what will be our goal over here to make it learn? So for that we will again, so x is our input which we already talked about. Now we will introduce another concept called a, that means the output over here, which is the current output. That means whenever our neural network will start learning, so what will be happening? So we will be starting with some input image x, and then we will be starting with some weights and biases here, right? Our job is to learn those weights and biases through gradient descent, correct? To like basically determine the optimal values of those weights and biases over here, correct? So that means if we just take these weights and biases, so our job is to find the weights and biases such that our output of the network A, current output, will be as much as close to the actual output yx over here. That means, so if we are providing an image of 9 here, so if we can find weights and biases from this network such a way that A is representing 9, our job is done, right? So to achieve that, we need to go through something. We need to introduce something over here, which is nothing but our cost function. So what it will be basically doing it? So it will basically determine the difference, basically how far we reached from the actual output, and then try to optimize it. Maybe this equation looks really hairy now. Maybe in the next video we'll try to analyze this guy. Okay, so here if you see, this C is our cost function. So this will basically drive this whole neural network calculations over here, drive the weights and biases over here to reach it optimized level. And here our W and B are the weights and biases, that particular collection or matrices, whatever. We'll talk about this one, how to represent it mathematically. And then N is my number of training input. If you see, like we are basically taking some kind of average over here, and then A is my output. So what we are basically seeing it over here, if you see, if we just talk about very intuitive way, from the actual output we are basically taking a minus, basically subtracting the current output. Remember, these all are vectors, right? So that's why if you see this pipe, double pipes over here, so this is nothing but the vector, the length of this particular vector over here. Maybe that is a very simple term. We'll see maybe geometrically how it looks like. And then we are taking some kind of squares. We'll talk about this one as well. And then we are taking sum through all the images over here, and then taking some kind of average over here to determine our cost. And this cost we need to minimize it, so that my actual basically the actual output will be very much close to the current output of our neural network over here. And if you see, this A is actually the function of weights and biases as well, because based on this weights and biases only we will be generating this particular output. I have not written it over here. I could have write it over here A as function of weights and bias. Maybe in the next video we'll talk more about this particular equation and then go further. Okay, so we'll learn like whatever concept required to understand this stuff, we'll learn on the fly as well. Okay, so hopefully this video was helpful, and at least we got the basic start, so that we from the next video onwards we can try to go deeper inside this one as well. Okay, so hopefully this video was helpful. See you in the next video.